Welcome back, everyone, to the deep dive. You know we love to tackle those tricky subjects, and today is no exception. We're going to be diving into the role of causation in physics. Now, you might be thinking, wait a minute, isn't physics all about cause and effect? I mean, that's like Physics 101, right?
Yeah, you'd think so, right. But it turns out that there's a whole philosophical debate going on about whether this idea of cause actually has a solid place in the fundamental laws of the universe, like the ones physicists use to describe everything.
Yeah, I mean, it feels so intuitive, like if I push this microphone, it moves. Cause and effect, right. But when you get down to the nitty-gritty, the super precise language of physics, things get a lot more complicated. So, to guide us through this very heady stuff, we're turning to the Stanford Encyclopedia of Philosophy. They have a great entry on causation in physics that really lays out this whole debate.
Definitely. It's a great resource, really dives deep into all the different perspectives.
So, for all you listeners out there, you're probably thinking about cause and effect all the time without even realizing it. Whether it's understanding why your friend is in a bad mood or, trying to make sense of big world events. But this deep dive is going to take us to a whole new level. We're going to be examining whether even the most fundamental science, physics, relies on this whole concept.
Right, and it might just challenge how you think about the world, like at its most basic level.
Exactly. So our mission, should we choose to accept it, is to unpack all those arguments for and against the role of causation in physics. We're going to be putting on our philosopher hats and exploring different viewpoints on what causation even means when you're talking about these mind-blowing theories of reality.
And remember, we're not here to give you definitive answers. The debate is still very much alive.
Oh, yeah, it's a lively one. But we want to give you the tools to understand this whole fascinating discussion. So let's get right to it. Right off the bat, our source points out that philosophers have different ways of approaching this whole question of causation. They have different projects in mind.
Exactly. And these different projects really shape how they view causation's role in physics. First up, we have the metaphysical project.
Okay, metaphysical. Sounds deep.
It is. It's all about the fundamental nature of causation. Like, what is it at its core? What makes it true that one thing causes another? And this is where we hit a major philosophical fork in the road between what are called Humean and non-Humean accounts.
Okay, Humean, like David Hume, the philosopher, what's their deal?
Exactly. Humeans, generally speaking, they see the universe at its most basic level as like a collection of simple qualities and relations. Everything's very local. They reject the idea of these big fundamental modalities.
Modalities.
Yeah, things like necessary connections between events or inherent powers that make one thing cause another.
So like a magical force that links cause and effect.
Kind of, yeah. Humans say, nope, not buying it. So for them, when we talk about causation, we're not describing some deep feature of reality. Instead, any talk of causation has to be reduced to these more basic, non-modal happenings in the physical world.
So no spooky action at a distance for the humans.
Not at a fundamental level, no. And even within this Humean view, there's a range of positions.
Yeah.
You have folks who think causation is useful, like a handy tool, but ultimately reducible to simpler things. They're called non-fundamentalists.
Okay, so it's there, but it's not like the bedrock of reality.
Exactly. And then you have the eliminativists. They're like, let's just ditch causal talk altogether.
Whoa, hardcore. So they just throw the whole concept of causation out the window.
When talking about fundamental physics, yeah, they say it just muddies the waters.
Wow. All right. So we've got the Humeans saying no fundamental causation. What about the other side? The non-Humeans, was it?
Right, the non-Humeans. They take a different stance. They argue that those modal properties, including causal properties, are actually baked into the universe, like fundamental ingredients. For them, causation isn't built up from other things. It's one of the primary building blocks.
So it's there from the get-go.
Exactly. And they have different ways of fleshing this out. Some non-Humeans, like Tim Maudlin, propose that the very laws of physics are fundamentally causal. Like the way the universe unfolds, it's inherently causal. Earlier states produce later states.
Okay, so it's not just a description. It's about how things actually happen.
Right. And then you have others, like Nancy Cartwright and Alexander Bird, who say that objects themselves have these fundamental causal powers or dispositions.
Like, objects are born to cause things.
In a way, yes.
Mm-hmm.
Like a particular kind of atom might have an intrinsic tendency to decay in a certain way because of its causal powers. It's built into its nature.
Wow, that's really interesting. So one side sees causation as derived, the other as fundamental. Makes sense. Now, you mentioned earlier a descriptive project. What's that all about?
Yeah, the descriptive project, it's a bit different. It's not so much about the deep metaphysical nature of causation, it's more about how we actually use the concept in our everyday lives.
Like how we talk about causes and effects in normal conversation.
Yeah. Exactly. Philosophers working on this project, they're trying to analyze our common sense understanding of cause. They want to figure out, like, what are the necessary and sufficient conditions for us to say that one thing caused another?
So they're basically trying to define the word cause, right? Like in the sentence, the lack of rain caused the drought.
Precisely.
Yeah.
And there are lots of theories out there, like regularity theories, which focus on patterns of events. Then there's Mackey's INUS condition, which gets pretty complex. And also David Lewis's counterfactual analysis, which is all about what would have happened if.
Okay, so they're looking at all the ways we use this word cause and trying to pin down exactly what we mean.
Right. And interestingly, this project has historically relied a lot on thought experiments and our intuitions about everyday scenarios.
Like if I drop a ball, it falls, that kind of thing.
Exactly. They haven't really focused on how the concept of causation is actually used in physics, though, more on our common sense understanding.
Makes sense. So we've got the metaphysical project and the descriptive project. Now there was a third one, the functional project, right? What's their angle on causation?
Right, the functional project. This one is all about what causal concepts do for us. What role do they play in our thinking, and how useful are they?
So it's not so much about what causation is, but what it allows us to do.
Exactly. And a big idea here is that causal knowledge helps us take action. If we understand the causes of things, we're better able to intervene and bring about changes.
Okay, so it's like if I know that the cause of this plant wilting is lack of water, then I know what to do to fix it.
Precisely. This idea is prominent in the work of philosophers like James Woodward and Nancy Cartwright. They emphasize that causation is crucial for making good decisions and achieving our goals.
Makes sense. And you mentioned something about conceptual engineering earlier. How does that fit in?
Yet conceptual engineering is all about looking at our concepts and seeing if they're actually working for us.
Like, are they doing their job?
Exactly. And if they're not, maybe we need to refine them or even come up with completely new concepts. So in the functional project, you're looking at our causal concepts and asking, are these the best tools for the job? Can we improve on them?
Okay, so it's like constantly evaluating and upgrading our conceptual toolkit.
That's a great way to put it. And this is where things get really interesting when we start talking about physics. Because now the question is, do our everyday causal concepts actually work in the realm of physics? Or do we need something different?
Right, like maybe our everyday notions of cause and effect just don't cut it when you're dealing with the fundamental laws of the universe. So we have these three different ways of thinking about causation, all with their own unique perspectives.
And all of them have something to say about the role of causation in physics. It's not like one project is specifically focused on physics. It's more that this question about physics runs through all of them.
Right, it adds another layer of complexity to the whole thing.
Exactly. And this is where we encounter some of the most serious challenges to the idea of causation in physics.
Oh yeah, the source mentioned these. I think they were called neo-Russellian arguments, right? What's that all about?
Right, neo-Russellian arguments. They're named after Bertrand Russell, the famous philosopher. He and another thinker named Ernst Mach were very influential in raising doubts about causation's place in physics. And their arguments have been picked up and developed by more recent philosophers. We call them neo-Machians and neo-Russellians.
So it's like a philosophical tradition questioning the whole idea of causation in physics.
Exactly. And they have a pretty consistent strategy. They basically say, okay, you think causation has this feature, but physics can't handle that feature. Therefore, causation can't be part of physics.
So it's a kind of elimination strategy.
Precisely. And they've identified a whole bunch of features that they think physics just can't accommodate.
Okay, so what are some of these deal breakers for causation, according to these folks?
Well, the first one is the vagueness challenge. They point out that our everyday causal language is often pretty imprecise.
Like if I say, stress caused my headache, what kind of stress? How bad is the headache? It's all a bit fuzzy.
Exactly. And compared to the super precise mathematical language of physics, our causal talk seems really vague.
Yeah, physics is all about equations and exact measurements. Vague doesn't really fit in there.
Right. Now, philosophers like Kirchhoff, Mach, Norton, and Ehrman have really emphasized this point. They argue that our ideas about cause and effect are just too fuzzy to be properly defined.
Or to play a role in this very precise science.
Exactly. They say that even when physicists use causal language, it's just shorthand. like a loose way of speaking. It's not part of the core, rigorous content of their theories.
Okay, so that's one challenge. What's the next one?
The next one is the dominant cause challenge.
Dominant cause.
Yeah. So think about how we usually explain things. We pick out a few key factors and call them the causes. Like the faulty wiring caused the fire.
Right, we're not talking about every little detail.
Exactly. We implicitly distinguish these dominant causes
Mm.
from all the other background conditions that were also necessary,
Oh.
like the presence of oxygen, flammable material, and so on. But the problem, according to these philosophers, is that in physics, especially if we assume it's deterministic, an event is the result of a huge, complex web of initial conditions. You can't just isolate a few of them and call them the causes.
So it's like saying that everything that led up to the event is equally a cause.
In a way, yes, it becomes really hard to draw a line between what's a cause and what's just part of the background.
And I guess this is especially true if you think about like the whole history of the universe leading up to that event.
Exactly. Bertrand Russell actually made this point really clearly. He said that if you take the cause to be the entire state of the universe at a previous time, then the principle, same cause, same effect, becomes kind of meaningless because that exact state of the universe is never going to happen again.
Right, it's a one-time thing.
Exactly. And if you try to narrow down the cause to just a few factors, well, then you run into the problem that those factors are themselves influenced by countless other things.
So it's like an infinite regress of causes.
Exactly. And this poses a problem for both the descriptive and functional projects, because the descriptive project tries to define our common sense notion of cause, which usually focuses on a few key factors. And the functional project emphasizes the usefulness of causal knowledge for taking action. But if you can't even isolate the causes, then how could you use that knowledge?
Right, it gets very messy.
Very messy. So that's the dominant cause challenge. Then we have the determinism challenge.
Determinism, like everything is predetermined.
Right. The idea that the same cause always leads to the same effect. No randomness, no chance involved. And a lot of traditional philosophical theories of causation are based on this assumption.
Okay, so what's the problem with that?
Well, the problem is that physics, especially modern physics, is not so sure about determinism anymore. Quantum mechanics, with its inherent probabilities and uncertainties, really threw a wrench in the works. But even within classical physics, there are some tricky examples.
Like what?
Like the famous dome example that John Norton, a philosopher of science, came up with. It involves a mass sliding down a perfectly symmetrical dome. And even in this seemingly deterministic system, there's a point where the mass's future behavior becomes unpredictable. It's really fascinating.
So even in a simple classical system, there can be this element of randomness.
Exactly. And Norton argues that this poses a dilemma for causation. Either causality puts limits on what can happen in the world, like a rule that everything has to follow, or it doesn't. If it does, we haven't found those limits yet. And if it doesn't, then causality is just a word we slap onto things without any real justification.
So it's either a rule with no clear content or just an empty label.
Exactly. And this creates problems for our understanding of causation, especially if we want to connect it to physics. Because if the world isn't deterministic, then this idea of same cause, same effect becomes really problematic.
Right. If there's randomness involved, then how can you say that the same cause will always produce the same effect?
Exactly. And this has led to some philosophers trying to develop accounts of probabilistic causation. Like, how can we talk about cause and effect in a world where things aren't completely predetermined? But even that gets tricky.
So that's the determinism challenge. What's next?
Next up, we have the locality challenge.
Locality.
Yeah, it's the idea that causes are local in both space and time.
Yeah.
So spatially, it means that a cause is usually something that happens in a relatively small area. Like if I push this microphone, the cause of its movement is my hand, not something happening on the other side of the world.
Right. It's a very localized event.
Exactly. And temporally, it means that causes don't act instantaneously across vast distances. There's usually some time delay, and the influence travels at a finite speed.
Okay, so there's no spooky action at a distance?
Not in our everyday understanding of causation, no. But the challenge here is that some fundamental physical laws describe influences that seem to act across vast distances, even instantaneously.
Like what?
Well, Newtonian gravity is a classic example. According to Newton's law, any two objects with mass attract each other with a force that acts instantaneously, no matter how far apart they are.
So it's like the sun is pulling on the Earth right now, even though it's millions of miles away.
Exactly. And that violates the temporal aspect of locality. Then you have quantum mechanics, which has its own weirdness with entanglement. Two particles can be linked in such a way that they influence each other instantaneously, even if they're light years apart.
Okay, that's definitely spooky action at a distance.
Right. And this poses a challenge because it suggests that maybe locality isn't as fundamental as we thought. Maybe there are genuine, non-local influences in the universe. And if that's the case, then our usual way of thinking about cause and effect, where things happen locally, might need to be revised.
So it's another blow to our intuitive understanding of causation. What's the last challenge?
The last major challenge is the time asymmetry challenge, and this is a big one.
Okay, tell me more.
So we have this very strong intuition that causes come before their effects. Time flows forward, and causes precede their effects. Effects never precede their causes. But the challenge here is that the fundamental laws of physics, at their most basic level, seem to be time-symmetric,
Meaning?
meaning that they work the same way whether time is flowing forward or backward. They don't have a built-in arrow of time.
So it's like if you could rewind the universe, the laws of physics would still work the same way.
Exactly. And this creates a puzzle. If the laws themselves don't distinguish between past and future, how can they give rise to a concept like causation, which is all about a specific temporal order?
Right, if the laws are time symmetric, then why does causation always go in one direction?
That's the million-dollar question. And philosophers have been wrestling with this for a long time. Some have tried to come up with symmetric notions of causation, where it doesn't really matter whether the cause comes before or after the effect. But that gets tricky when you try to explain things like intervention, responsibility, and explanation.
Like if I break a window, it matters that I did it before the window broke, right?
Exactly. And it's important to note that not all fundamental laws are perfectly time-symmetric. There are some subtle exceptions in particle physics, but still, the general picture is that the laws themselves don't seem to enforce the kind of time asymmetry that we associate with causation.
So that's a pretty big challenge.
Huge. And the source goes into some specific examples of this, like Green's functions. Have you heard of those?
Vaguely. They have something to do with waves, right?
Yeah, they're mathematical tools that physicists use to describe how a disturbance spreads through a system over time. Like imagine you throw a stone into a pond. You see the ripples spreading outwards from where the stone hit the water.
Okay, I can picture that.
So a causal Green's function would describe how that disturbance propagates forward in time. But here's the thing. For certain types of wave equations, which are time-symmetric, the math allows for solutions that look like ripples converging inwards towards a point before anything happens there.
So it's like the ripples are traveling back in time.
In a way, yes. And these are called anti-causal or advanced Green's functions. And the problem is that if you try to interpret these advanced Green's functions causally, it means that the effect, the disturbance, actually happens before the cause, which is, of course, a big no-no in our usual way of thinking about causation.
Yeah, that totally messes with our intuition about time and cause and effect.
Right. And since both types of Green's functions are mathematically allowed by the time-symmetric laws, it's hard to say why we should only consider the causal ones as physically meaningful.
So even the math itself seems to allow for scenarios that violate our sense of cause and effect.
Exactly. And it really highlights this tension between the time symmetry of the fundamental laws and the time asymmetry of our concept of causation.
This is all very mind-bending. Now, what about the role of initial conditions in physics?
Ah, that's a crucial point. So physicists often focus on the laws of physics, like Newton's laws of motion or the laws of thermodynamics. But those laws only tell you how a system changes over time. They don't tell you what the system was like at the beginning.
Okay, so you need a starting point.
Exactly. You need initial conditions. And these initial conditions are really important because they can actually introduce a kind of asymmetry into the system.
In what way?
Well, physicists often assume that the initial state of the universe or of a particular system was very random or chaotic, like things were just spread out and jumbled up. But as time goes on, and the laws of physics do their thing, the universe tends to become more ordered and structured.
So it's like going from a messy room to a tidy one.
Exactly. And this process of going from randomness to order is often associated with the thermodynamic arrow of time.
Okay, so the universe is becoming more organized over time. How does this relate to causation?
Well, it brings in this really interesting concept called common cause reasoning.
Common cause reasoning.
Yeah. So imagine you observe two events that seem completely unrelated, but they happen to be correlated. Like, let's say you notice that every time the ice cream truck plays its music, your neighbor's dog starts barking.
Okay, that's a weird correlation.
Right. Now, common cause reasoning says that if we see a correlation like that, it's often because there's a common cause in the past that explains both events. Like maybe the ice cream truck driver always rings a bell right before playing the music, and that's what triggers the dog to bark.
So it's not that the music itself is causing the barking, it's this third thing, the bell.
Exactly. The common cause, the bell, explains both events, and it screens off the correlation.
Meaning?
Meaning that once you know about the bell, the correlation between the music and the barking doesn't seem so mysterious anymore.
Okay, so it's like the bell is the real cause, and the music and the barking are just effects of that cause.
Exactly. And this kind of reasoning is really common, not just in our everyday lives, but also in science, like in physics.
Really? How so?
Well, the source actually gives a really cool example involving the detection of gravitational waves. So back in 2015, physicists announced that they had finally detected these ripples in spacetime that Einstein had predicted.
Yeah, that was a huge deal.
It was. And the way they detected them involved these incredibly sensitive detectors located thousands of miles apart. And what they found was that the signals from these detectors were perfectly correlated, like exactly the same pattern of waves arriving at both detectors at the same time.
Wow, so it wasn't just random noise.
Exactly. And the only plausible explanation for this was that there was a common cause, a single event, that had sent out these gravitational waves, and they had traveled across the universe and reached both detectors.
Hmm.
And what did they infer this common cause to be? The collision of two black holes, billions of years ago.
That's incredible. So they used common cause reasoning to figure out that these black holes had collided.
Exactly. And the key here is that they relied on the assumption of an initially random universe. Like, if the universe wasn't random at the beginning, then maybe those two detectors just happened to pick up two independent waves that just happened to be perfectly correlated.
Right, but that seems super unlikely.
Incredibly unlikely. So the common cause explanation is much more plausible. And this whole idea of common cause reasoning, it has this built-in time asymmetry.
In what sense?
Well, we always infer a common cause in the past to explain correlations in the present. We don't infer common effects in the future.
Right, it's always about something that happened earlier.
Exactly. And this seems to suggest that maybe causation itself has this inherent time asymmetry, even if the fundamental laws of physics don't.
So maybe the arrow of time, the direction of causation, is somehow built into the universe, even if it's not explicitly in the laws themselves.
That's one possibility. And there's a lot of debate about exactly how this works. Some philosophers think that this initial randomness of the universe is the key. Others think there's something more fundamental going on. But it's definitely a very active area of research.
Wow, this is all so much to wrap my head around. So we've got these five major challenges to the idea of causation in physics. The vagueness challenge, the dominant cause challenge, the determinism challenge, the locality challenge, and the time asymmetry challenge.
Exactly. And they all raise serious questions about whether our intuitive concept of cause and effect actually fits with our best understanding of the universe.
And it's not like there are easy answers.
Not at all. This whole debate is still ongoing. But there are a bunch of other really interesting perspectives out there, too.
Oh yeah, the source mentioned some of those, right?
Right. Just to give you the taste, there are interventionist accounts of causation, which focus on our ability to manipulate things and see what happens. If I can change X and it leads to a change in Y, then maybe X is a cause of Y.
Okay, so it's about experimenting and seeing how things are connected.
Exactly. Then there are conserved quantity theories, which try to ground causation in the transfer of things like energy and momentum. Like, if I hit a billiard ball, I transfer some of my energy to the ball, and that causes it to move.
So it's about tracing the flow of these physical quantities.
Right. And there's also a lot of discussion about the connection between causation and entropy, which is a measure of disorder in a system. Like, how does the thermodynamic arrow of time, the tendency for disorder to increase, relate to the arrow of causation?
Right, because the universe seems to be getting more organized over time, not less.
Exactly. And then there's the relationship between causation and radiation, which has its own set of puzzles. And of course, there's the whole issue of causation in quantum mechanics, which is a whole other can of worms.
Right, because quantum mechanics is already so weird and counterintuitive, so it's not surprising that it would mess with our ideas about causation, too.
Exactly. But all of these different perspectives, they show just how rich and complex this whole debate is.
Yeah, it's definitely not a simple question. So, as we wrap up this deep dive into causation in physics, what's the big takeaway for us?
I think the big takeaway is that the role of causation in physics is far from settled. It's a deeply philosophical question that forces us to think really hard about what we mean by cause and effect. And it also shows how intertwined physics and philosophy really are.
Yeah, it's not just about equations and experiments. There are these big conceptual questions that physicists and philosophers are still grappling with.
Exactly. And for you, dear listeners, we hope this has given you a new appreciation for the complexity of this seeming simple concept.
Yeah, cause and effect might seem like common sense, but when you really dig into it, it's anything but.
Absolutely.
Yeah.
And it makes you wonder, does our reliance on causation reflect something fundamental about the universe? Or is it just a useful way for our brains to make sense of the world, even if it's not a perfect representation of reality?
Right, like maybe causation is just a story we tell ourselves to make things easier to understand.
That's one possibility. And it's a question that's still up for debate.
So if you're interested in exploring this further, we highly recommend checking out the Stanford Encyclopedia of Philosophy entry on causation in physics.
And maybe read some of the work by the philosophers we've mentioned today. There's
Yeah.
a lot of fascinating stuff out there.
Yeah, this is definitely a topic that can keep you thinking for a long time. Thanks for joining us on this deep dive.